All right, let's get started. All right, so this is the last lecture that I'm going to be giving, and then Natasha will give a guest lecture on Tuesday, and there'll be paper discussions on Thursday. I just sent out assignments just now. Yeah. Sorry. Yeah.
Like up
till I think June 11th or something is when I have to enter in grades, and so yeah, just yeah, don't push it beyond that. But feel free to use it. Yeah, so homework 3 is due on the 31st, I believe. Right, and then presentations on the 4th. And yeah, I think paper discussions, I sent it out to everyone. If you didn't receive, it's also on EdSTEM, so just make sure that you are up to date. Cool. All right, and then there's free donuts for you guys. Just feel free to grab them after class.
Is it just like a poster session or is there also like presentation?
No, just a poster session. And I think we'll just cancel the final report. It's fine. Just a yeah. I'm lazy too. So I think we'll cancel the final report, just do the poster session, and if you're not here, send me a recording. That's it. Great. Okay, so let's get started. Today we have finished most of things, and I did edit this schedule a little bit to backfit what we're actually going to do, but today we're going to do learning across tasks. So we're going to study multitask and meta reinforcement learning, and then I'll try to provide a bit of perspective on all of the whole course and what we learned and what to take away from it. And so today we're going to think about how do we go from single task to multitask reinforcement learning. And so when we say single task reinforcement learning, you typically want to do one thing, but from many different configurations. Let's say you're trying to rotate this pen, you're trying to rotate it from many different initial positions, but always rotate it to the same target, let's say, right? And then like, let's say you have a humanoid, you want to like have it do like flips or something, right? You want to do a single task, but you want to go from there to trying to do multiple tasks, right? So let's say this is a gift from this benchmark meta work where they try to do 50 tasks, which are related in a way, right? So they're like the same robot, but they're trying to do different things. And so single task RL is typically trying to do the same thing, and multitask RL is trying to do different things. And the line between them is a bit blurry, right? You can say that like going to many different configurations is also multitask, but often that gets lumped into single task. And so the line is a bit blurry because like the line between configurations and tasks is not very clear, but typically when we say multitask, we mean something like that, where the like, you can clearly see that those are trying to do different things, right? But it's the same action space and often the same state space, right? And so what we're going to try and do is take a lot of the algorithms we've discussed so far as a single reward function to try and do a single task. So they're in this setting, we're going to try and build algorithms for this. Whether that's like directly zero shot, like you ask it to do one of the new tasks directly, or whether you like do it with a little bit of fine tuning, right? Both settings work. So what we're going to try and figure out is how do we make RL algorithms generalists. So far we've talked about building specialists, but we want to build a generalist. So you have a single agent that can quickly or in few shots solve many different tasks. Okay? And so we want to think about specialist RL takes in an observation. There's some planning, reasoning, whatever, or just policy, which gives you some behavior, some actions to take in the world. When you talk about a generalist, you want to say the same agent can do many different tasks. So you want to say you take an observation, you take in a specification of the problem you care about, you want to produce behavior, you want to produce an action or a plan or something else, right? But it's kind of the real premise of generalist RL is generalization to new problems, right? So we're going to talk about two settings, multi-task RL, which is more about solving many tasks with the same agent, and meta RL, which is about solving new tasks quickly, right? And so they're related, but not quite the same. So in multitask RL, the framework we're going to think about is the following, right? So normally you have an MVP, you have a state space, an action space, transition dynamics, reward, and an initial state distribution mu, and discount factor gamma, right? That's the typical definition of MDP. Talked about a bunch of things to maximize the reward in this set. Now, in multitask situation, you have a distribution over MDPs, right? So let's say you have many different MDPs, each with the same state and action space, but with potentially different transition dynamics, DI, potentially different rewards RI, and then you have a distribution over these tasks, P of MI, right? And so the point is, rather than just having a single MDP, you're going to have many different MDPs, and these MDPs are going to be drawn from some distribution.
So does that mean, number of M's could be like
Infinite, yeah. So in practice, it's hard to do that, right? In practice, you like typically will have a setting that looks like, like that, right? Where you have like, you make up some number of tasks, right? But in principle, as long as you can sample from this MDP, then you can generate new tasks, right? So this is more true in some domains than others. So there's, for instance, a domain called ProcGen where people just like generate video games. They like have procedural code that generates video games. You can generate infinitely many video games. But if you're trying to come up with robotics tasks, you can only generate so many. Well, I think people are coming up with ways to generate more, but right now you like make them by hand, right? And so, yeah, you're right that often, like in some settings, you can do infinite. In many settings, you just have a finite sample, right? But one thing to note about multitask is that it's often hard to know what a distribution of tasks means and whether new task distributions are the same as the old ones, right? Like, how do you know if picking up a basketball is the same as like throwing a javelin? Is like not clear, right? Or if it's from the same distribution rather. And so one thing that I think is an interesting open question is like characterizing task similarity and like characterizing whether this assumption of like being from the same distribution holds, right? So a lot of the domains that people do for multitask and meta-RL, they like artificially manufacture these distributions. They like say, okay, like you have to go here and here and here and here and here. Or you have to pick up cubes of like sizes where you vary the parameter of the shape or the size. Right? But they like artificially construct them so that it matches this distributional assumption. In practice, that may or may not hold, right? And so I think that's an interesting research question, but for now, we're just going to assume this. Yeah. It's a great question. It's hard to characterize relevance. And so here, all we're going to assume is that the training tasks and the testing tasks are drawn from the same distribution. But we're not necessarily saying that elements of the distribution are relevant to each other or not, right? But yeah, I think that's like an interesting research question to ask. Okay, so we're just going to assume that training and testing tasks are drawn from the same distribution. And we're going to have the same state and action space so that you can have the same policy run, right? If you have a very same action space, it's hard to run the same policy in all those settings, right? Yeah.
I think specifies a reward.
Yeah, that's a great question. There's different ways of doing it. Like the multitask RL will try to have like a task specifier, whether it's through language or a task ID or something like that, or a goal image. In meta reinforcement learning, you typically specify new tasks through the reward function. So you can just like provide rewards according to the task you care about, and that's how you specify. So our goals for today are to like try and study this multitask reinforcement learning setting and try to think about whether we can just take all the same techniques that we used earlier and just like throw them in here, or do we have to invent new things? And then try to like think about like what are the practical challenges in building these types of generalist multitasking. Okay, so that's what we want to do. And the natural question to ask is why should we do this, right? So yeah, why should we do this? Like, why can't we just like run RL for every new problem?
I think because there's a lot of third mileage that could be reused in a bunch of different tasks.
Right.
And
Right. Yeah. So I mean, if RL is taking the order of millions of samples, I don't want a household robot to like, punch a hole through my wall if it's fine-tuning with millions of samples. So it's kind of, to me, it feels like kind of the only way to be practical is through multitask learning of some sorts, right? You can't really hope for single task learning to work in practical deployment settings. And the hope is that, as Yushan was saying, like there is some relevance between the tasks, and that relevance lets you share information, right? And so the hope is that we can generalize immediately and quickly to new unseen tasks. The other reason is that if we develop algorithms that can learn quickly in new problems, like you can think about generalizing to new settings, which is really the goal of most machine learning, right? So far in reinforcement learning, we have not talked about generalization at all, right? Like we basically said, there's a function approximator. The function approximator is mainly just to deal with continuous space, but nobody's really trying to generalize, right? But the hope with multitask learning is really about generalization. The same way that inverse RL is about generalization, multitask RL is also about generalization, right? So like we're going to talk about some algorithms that don't really generalize to start with. Those are not the ones you should think about. We should really think about generalization to go forward. Okay, any questions about the setting? Okay, let's keep it. So the outline today, we talked a little bit about like the problem setting to go from specialist to generalist. We'll talk about a class of learning methods called multitask reinforcement learning methods. We'll then talk about a class of methods called meta reinforcement learning, which is related but a little different. Multitask is trying to deal with the optimization problems of solving many tasks at once. Meta RL is really concerned with dealing with the K+1 task. And then we'll talk about some takeaways. Right? Great. So to kind of formulate the multitask setting, we're going to construct a meta MDP, right? And this meta MDP is going to say that like there's going to be some context omega I that is going to like characterize every problem, right? And so, for instance, if it's like your multitask is going to different positions in the space, like your omega I is going to be like, what is your goal position that you want to go to, right? So we're going to assume that we have access to some sort of context that is characterized by omega I, where that could be like a task ID, a goal, image, or state, a video describing what you want to do, a language instruction, all of those satisfy the criterion. But the point is that your transition dynamics and your reward can depend on this, and then you have a distribution over these, and that gives you your task, right? So it's hard to like get distribution of MDPs because they're like MDPs are like a nebulous mathematical object, but we're gonna say there's going to be some vector omega I, which is going to characterize the difference in your task. It's a sufficient statistic for the differences in your task, and it's going to be some vector in Rn, right? And that is going to be able to parameterize the differences in dynamics and reward. Yeah. Okay. So under that formulation, what we can think about is changing our state space to be an augmented state space. Your state space will have the original state space S along with your context vector omega I. We're going to assume that is known. Like someone tells you what you want to do. Right? That's Raymond is saying. How do we know what we want to do? We're going to say someone tells us, right? And so we can say the state space is S omega I. The transition dynamics now becomes conditional on omega I, and your reward becomes conditional on omega I, right? And so in this reformulated space, now it becomes the same as an MDP. It's just an MDP with a bigger space, right? Now, given this kind of formulation, the main point we're trying to make is that you can solve multitask RL as a single task RL in an augmented MDP, where your MDP includes your state as well as your context vector, right? Just like the simplest thing you can do is just add it to your state. Your policy now takes in state and context vector and just run RL as usual. Right? And we'll talk about why that's maybe not going to work, but the point here is from a like type matching perspective, all you need to do is just augment your task specification to your state, and you can reuse all of the same machinery that we had earlier, right? And so what we can start with is think about this meta world domain. We want to solve all of these. Let's say you're just given like a task ID, right? So you're given a task ID from 1 to 50, and you just augment the task ID to your state. And so now your state is position of the arm and position of the objects and maybe an image of the scene, as well as the task ID, which tells you what you want to do. And then you just run active critic, same as usual. The only difference is that you're going to have an expectation over tasks, right? So the way you do it in practice is that you're going to like sample a batch of tasks, and for each of the tasks, you sample a batch of data, and then you just reapply the same thing. So you just put like an outer expectation, right? Where your batch will include multiple tasks at once. Right? And so it's important to do that and not just do one task at a time, because you'll start forgetting between the tasks, but it's kind of the same framework. And so your policy and your key function look similar. You just going to take in a state and a task ID, state action task ID, and everything remains the same. Okay, so seems like an easy recipe, right? All we're doing is We're augmenting the state. We're running the same types of algorithms, right? And so the template for multitask RL, you sample data from all the tasks using the same actor, but with different task IDs according to the tasks that you sample. Collect all the data into a single batch, right? The state will just be augmented. And then you perform standard actor critic updates with losses summed up across all the tasks, right? So every update remains the same actor, same critic. I don't know why I changed the notation, but that should just be omega, right? So the machinery is the same. Does it work, right? The natural question to ask is, does it work? And we tried it on these meta world tasks, and we saw that like if you try to train all of the tasks together, it's multitask SAC, right? Really, it should like each of the tasks is solvable. It's 100% success. But if you train them together, it's 28% success. And you do a little bit of fanciness, you can get up to 35% success, but it's like much worse. So, like this is a single task, and this is these are multitasks, and like the gap is huge. Right. So that suggests that multitask optimization is not as simple as just sticking in a task ID and just like running the same algorithms. You have to do more, right? And so when we studied this in like 2019 maybe, and when we did it, we were expecting that this would be trivial. We just add in the task ID, you do SAC as usual, but we found that there's like strange optimization issues that happen that makes multitask RL hard, right? So if you're ever trying to run RL across like really wide initial state distributions or lots of different tasks, you'll find that multitask can often be harder even without generalization. Even if you just want to solve the 40 training tasks, it's just really hard to optimize 40 training tasks to solve the same thing. And let's try and study why, right? So this is mostly a hypothesis, right? But the thought is that when you're solving many different tasks together, you have gradients for different tasks that might be conflicting with each other, right? And when you're trying to interleave conflicting gradients with data collection, that's when multitask RL gets hard, right? So the thought is that, you know, you have like one policy, right? And then gradient for task one takes you this way, right? And gradient for task two takes you this way. And normally that's fine. That's true in like any supervised learning problem too, right? People do supervised learning with multitask learning that works just fine. I think what becomes tricky is when this is coupled with exploration, right? You're like collecting data. And the problem is these gradients are conflicting, right? What might happen is that, okay, like this, we take a step in this direction and less in this direction. And then we like kind of stop exploring for this guy, right? And then we get worse data. So this keeps getting worse and worse and worse and worse. And so what you tend to have is like this winner takes all type phenomenon when you're training multiple tasks together. And so the point I want to make is that a combination of gradient conflict and exploration leads to like problems in multitask optimization, right? And so the thought is that when you have gradients pointing in two different directions, which will often happen with different tasks, like the way you want to pick up a basketball versus pick up, you know, a laptop might be different, right? But it's okay if you're not coupling with exploration, it resolves itself. But if you're coupled with exploration, you get this like winner takes all problem. And it's not that it's a representational issue, like as we saw that the policy has the task ID included. So in principle, it should be able to represent the optimal policy because the task ID allows your things to separate, right? It's just that it's really hard to find that optimum. And so when we're dealing with this like combination of conflicting gradients and exploration, that's when you get into trouble, right? So some homework for y'all is there's this paper called Ray Interference. That's from some folks at DeepMind, which I think is a wonderful paper. Which kind of like tries to study this in toy problems. And they show that even in like bandits problems, this happens as long as you're like coupling together conflicting gradients and exploration. Ray interference, ray like light rays interfering. But they argue that this is often the reason for instability in deep RL, in that you like have this winner takes all phenomenon where you're like good in certain places and bad in certain places because of the gradients conflicting with each other. Okay, so this is sad. And we need to like develop good algorithms that can deal with this problem, because you can't like get rid of the multitask problem, right? And so we need to ask the question, how do we deal with gradient interference in RL when we combine exploration and conflicting gradients, right? So yeah, how do we deal with it? What are some ideas? So the problem is you have multiple tasks, gradients are conflicting with each other, and you couple it with exploration, it's going to lead to suboptimal outcomes on all the tasks. How do we, like, what's one way to deal with this problem? And the goal is to learn a single agent that can solve all the tasks. No generalization for now. Just the training task. You just want to have a single agent that solves all. Like, what are some ideas that we can think about to deal with it?
I think might be a dumb idea, but like what if you did like ensemble different policies?
Yeah, so one of the ideas is similar to that, but an ensemble of different policies where you train them across all the tasks. Each of the policies is a multitask policy. Is it an ensemble of multitask policies? Of single policies, yeah. I think, yeah, so that'll probably work. But then the question we should probably ask is, do we get any benefit of, like, that's like almost like saying train a mixture of experts. You just have K experts and then you just like pick which one you want to deploy, right? Do you get any benefit of training multitask things versus just single task things, right? But yeah, it's a good idea. Yeah.
Maybe like teach it one task at a time.
Right. So continual learning. The tricky part about continual learning perhaps is that you forget things, right? So you're at the you're at the 10th task, you might have forgotten the first task. And so like, I think it makes sense that you do one task at a time, but you have to be careful not to forget old tasks. So I think it'll help with some issues, but it'll lead to other issues that come up.
You like instead like mini batches, so you like do a bunch of one and then do a bunch of another.
I think that has the same forgetting problem. Yeah. Yeah.
That'd be a way to separate the tasks. Train like part of the network to do one task and part of the network to do another task. And it kind of like final several layers that is doing the
Shared.
selection for you,
Yep.
figuring out which of the experts you should trust.
Yeah. That sounds a bit like Raymond's suggestion here, right? That's
Like
often how
what you said
people do
about
things.
them.
There's like a nice line of work called PathNet and ModuleNet and these kinds of things which try to do this. Basically, they have like modules that you select. You have a coordinate, you learn a coordinator, and you have modules that you select. So not every task activates every module. And that tends to work. Yeah, that's a good idea. Yeah.
You will find some like mapping that represents all the classes in the domain where gradients
They don't conflict. Yeah. So that's kind of one of, yeah, I think you guys have basically covered both the solutions. But the first idea is we're gonna like, if the issue is that, I'll say how it's connected in a second. If the issue is a combination of exploration and conflicting gradients, the first idea is remove exploration. The second idea is remove conflicting gradients, right? And so the first idea is essentially similar to the things that Raymond suggested, where you try to train single agents that can do separate parts of things, but then kind of combine them together, but not with exploration in the mix. So kind of decouple multitask learning and exploration. And the second idea is like what Sanjay just suggested, like try to find a way to deconflict the gradients so that they like you can still make learning progress without getting stuck in this like winner takes all loop. Okay? And so we're gonna try and discuss two different ideas, removing exploration and modifying gradients.
You move array like that. How do you, like, doesn't that just corrupt one of the gradients then?
Yeah.
Like, how do we know which direction to move it in? We just sort of like average them together and.
We'll talk about it in more detail. Yeah. Okay, so the first idea is easy. It says that multitask supervised learning is stable, right? You're like, when you have multiple tasks, let's say multitask imitation learning, no RL, right? It like tends to work fine because you're not coupling in exploration. It's just that multitask RL is hard because you've coupled exploration and multitask learning, right? And so we're just going to say, do them separate and take these two insights, right? That single task RL is easy, multitask supervised learning is easy. And so we're going to try doing single task RL, bring them into a single policy using multitask supervised learning. Right? And so, so the idea here is that you can convert multitask RL into a bunch of single task RL problems plus a multitask supervised learning problem, right? So you're doing exploration with single tasks, and then you're combining it into a single policy with multitask supervised learning. So no exploration, right? And that tends to like, that basically removes this like mix of conflicting gradients and exploration. And so there's a bunch of papers in like 2018, 2019 that kind of try to do this, but it's saying that you divide a task into multiple, you divide like a multitask problem into multiple single task problems or smaller subsets of multitask problems, train each of them separately, and then distill them into a single solution, right? And so there's a graphic I stole from DeepMind because they have nice graphic designers. But basically, they have multiple different tasks in DeepMind Lab, right? And they say you're going to train multiple different policies individually, and then you're going to try and distill them into a single shared policy with supervised learning. And the point is made to Raymond earlier is like, why would I even learn the task together? The important part is that you're going to like inform the single task learning also with a shared policy. So you're going to go single task RL distill, and then the distill policy is going to like affect the single task learning to make it more efficient. And so let's talk about the details here. But the point here is that we're going to solve single task RL with standard reinforcement learning and distillation with multitask supervised learning. Yeah. And so the details here are basically this equation, which we're going to break down step by step, right? So it's saying that you have an objective where you learn multiple individual per task policies and one shared multitask policy, right? So the shared multitask policy is pi naught, and the per task policies are pi 1 to n. Yeah. We're going to try and optimize those per task policies to be optimal for each individual task. We're going to try and distill it into a single shared policy, which is optimal across all the tasks, right? And so your objective looks something like this. The first term is just per task reward. The second term is like this distillation term, which we'll break down in a second, but it's trying to like match the per task policy to the shared policy. It's trying to make them as close to each other. You can think of it like the KL divergence between the per task policy and the shared policy, right? And then the last term is just entropy, right? And so what we're trying to do here is that the first, like you can think of it as an alternating optimization where you try to optimize this objective with respect to pi 1 to n, and then you're going to try and optimize this objective with respect to pi naught. So it's like coordinate ascent, right? Where you optimize the n individual policies, and then you distill it into a single shared policy just by alternating the optimization on the same objective. Right, so let's try and understand why this makes sense. So you can think of this as a KL divergence. You can think of this as like single task RL, right? And then this one is just entropy, doesn't matter. So the point here is that if you consider optimization of this objective with respect to just pi I, right? I just think about this objective with respect to pi I, which terms depend on pi I? The first thing is like, this term depends on pi I. It's just single task reward, right? And the expectation with respect to pi I, so just like single task RL as usual. The entropy depends on pi I, that's just like maximum entropy RL, same as usual. The only thing that's different is this thingy, right? And this thingy is just saying, try to minimize the KL divergence between pi I and pi naught. That's right. That's all that's saying, right? So it's saying that like it's going to get penalized for deviating really far from what the shared policy would do, right? And so essentially that's just saying that like, let's say your shared policy did something and you're like changing your pi 1 to like some pi 1 prime. You're just saying that like, don't let these things go too far from each other, right? So it's like regularizing your shared policy, regularizing your individual policy improvement to not be too far from the shared policy. And that lets you like transfer information from this task to this task, right? So it's like, that's how the shared policy affects the individual policies. So this is what's going to make it more efficient than if you just train them all individually, right?
Like PPO, can we use click objective to do it instead of doing plot?
So clipping, you're saying like just like the problem with clipping is that it like you can do clipping, but you're still gonna have to do some density ratio, right? So maybe clipping will make it more efficient, but you still need to have some density ratio between the shared thing and the not shared thing. So clipping could certainly, right now what it's saying is that this is the old policy and the new this is the like shared policy, this is the individual policy, and you're like letting it go as far as you want. You're kind of saying like clip it. So it doesn't go past some level. You could certainly do that, but you're still going to have some sort of density ratio to like constrain. Yeah, good point. And then the other side is like much easier, right? But yeah. So yeah, I think this pi naught is going to like take in like your task ID or your omega. Good question. And then the second term is super easy. It's just saying like when you optimize this objective with respect to pi naught, right? Like this term doesn't matter. This term doesn't matter. The only term that matters is expectation pi I of minus log pi naught, right? So it's just going to be expectation pi I. Like notice that there's no pi naught here. There's no pi naught here. Like the only term that matters is expectation pi I of minus log pi naught, right? Which is just supervised learning. Just maximum likelihood supervised learning, right? So just saying like for data from each of your individual task policies, maximize their likelihood under the shared policy. So just doing multitask supervised learning, right? So just like I was saying earlier, we just need to add a task ID in there, right? And then we just do supervised learning, right? So the nice part about this objective is just to coordinate ascent, and coordinate ascent lets you do like single task RL, but regularized against a shared thing, and multitask supervised learning. You just you get the benefits of both. And so how well does this work? If you look at some learning curves, these are multitask in the sense that they're like really wide initial state distributions. And so they divided them into little regions, learn individual policies in little regions, and then distill it into a shared thing. And you can see that like DNC is probably DNC and centralized DNC are the ones that they propose, which are like significantly better than just a single task policy trained across everything, right? So you get like significantly better asymptotic performance and faster learning rate, even when it is improving slow. So yeah, it's super easy idea, just saying like mixture of experts, but keep distilling it and then regularizing individual training things against the shared policy. Okay. Here's some nice videos of tasks that they did, which I thought were fun. And they were trying to like do catching with an arm. And they found that you can do significantly better catching over a wider range with this kind of algorithm. They try to do like stair climbing and stuff with different heights of stairs and so on. And some tossing stuff. And yeah, that was a fun set of experiments. All right. So as we were just talking about this largely that like you can choose how often you distillation versus individual learning, but a lot of the learning is done individually per task, and the regularization.
Why did they choose those particular examples, like what's multitasking?
What's multitask about them? Well, these are the ones that had the nicest videos. But like for instance, the results back here. These ones are like across multiple different like tasks in the meta world benchmark. And so these are across 10 of these meta world benchmark tasks, which are like more different, if you will. It's just that the people like this wasn't a paper that I did. This divide and conquer distillation stuff. They just chose to do these tasks because even in these tasks, it's like across many different goals, many different initial states. And if you like optimize something across enough different goals and initial states, it also becomes a hard optimization. And so it's multitask in that sense. That's why I think the line is a bit blurry, but it's multitask in the multi-goal sense. Good question. Okay, so the challenge here is that we're doing a lot of individual learning, and you're like regularizing sometimes against the shared thing, but a lot of it is individual. And so we wanted to ask, can we do better than that? Can we do things that actually optimize a single policy, but not have to deal with this like winner takes all phenomenon, right? And so we were thinking about whether we can directly modify the gradients, right? The thought was that when you have conflicting gradients, that leads to this winner takes all phenomenon, but what if we just deconflicted the gradients, right? So the thought is, if you have two gradients with negative dot product, which means they're pointing against each other, what if you just deconflicted the gradients and replaced gi by some gi prime and gj by some gj prime, right? And so the idea that we thought about next was that when gradients conflict, project them to deconflict, right? And so what does deconflict mean here? It just says that if you have gj and gi, they're conflicting, just like project them onto the normal, right? And so you're saying that you're modifying the gradient, right? You're modifying the gradient. You're saying that you're no longer going to step in this direction, but you're going to step in this direction, which now no longer conflicts with this guy, right? And for this guy, you can say it's conflicting with this guy, so you're going to step in this direction, which no longer conflicts with this guy, right? And so the thought is that if I can deconflict the gradients, yes, I'm going to be losing, like the gradient is the direction of steepest descent, right? So you're going to lose some like learning efficiency, but you're not hurting the other tasks as much, right? So it's like this paper is called Gradient Surgery for Multitask RL, but literally what you do is you take the gradients and you like see if they have a negative dot product, you project it onto the norm. And then the reason it works is like it has a slower convergence rate, but it's not going to hurt the other tasks, right? And so you can show that it like in situations where the tasks are conflicting and there's like the Hessian has like a large enough eigenvector, this like could provably help, right? And so the thought is that all you do is that you say, if the gradients are conflicting, then you just project them onto the normal. And if the gradients are non-conflicting, then you just leave them alone, right? So if their dot product is positive, leave them alone. If they're negative, then you project onto the normal.
Isn't it between like projecting onto the norm and just adding the two gradients together and take them like that?
So if you add the two things together, then you like go here, I suppose, right? Which is a little different than saying you're gonna like project this guy on, like adding the two gradients together is what you'd normally do, right? But here what you're saying is that you're gonna like manually move this thing over here, so you're like this and this are not conflicting with each other, right? Whereas if you just added them together, that's what normal gradient, multitask gradient descent would do. Yeah.
Do we choose one of the two? Like,
You do it on both.
Then aren't we doing after? Do we
Then you just add the gradients and then you do gradient descent.
run projection
Yeah.
of G on and projection of the
That's right.
What happens if you do projection of the two? Getting projection of n, a normal vector on G, and then projection on ni, on projection of Gj. And so you're gonna have two this vector. What happens if you do projection of these two vectors instead of adding them?
We didn't try that. That's a reasonable thing to try, I think. Yeah, that's a good question. I'm not sure. But we could totally try that. Yeah.
But adding some more.
Well, that's the one we tried and it worked, but yeah, I'm not sure what happens in Berkeley if you try that.
It doesn't really, why does it make sense to project them onto normal planes?
Oh, just because then they're not conflicting with each other, right? They're like orthogonal.
You're just,
So like taking steps in one direction doesn't hurt the other one. Right?
but there's no guarantee that the direction can,
Because you're not like you're not going completely opposite, right? So you're saying that if they're in the same direction, leave them alone. If they're opposite directions, you project. You're never like impeding all of the progress. So you're still making some progress. It might be a little slower, but you're still making some progress. Some of this argument is empirical too, but
add the projections, will that be pointing in the same direction if you were just add?
I don't think so.
With the larger magnitude?
I don't think that's true, right? Because you'll have like what G1 minus G1 dot G2, G2, and G2 minus G1 dot G2, G1, G1. Like I don't think those are, the denominators are not really the same. So is that? I don't think that is true.
I guess just like visually, it kind of looks like.
Yeah, I mean, the visual is a little confusing because it's like all of them are kind of in, in the middle, but I don't think they're quite the same.
Okay.
I think as long as the magnitude is a bit.
Yeah, then it's different, right? Yeah.
Ultimately, you can only take one gradient step, so you project I onto J,
Yeah.
J onto I.
Then you take one
different things,
Yeah.
and then you add those.
Yeah.
What happens if you have like K different tasks?
We just do it pairwise, yeah. Yeah. Which is inefficient. It'd be good to come up with something better, but we just sample them and do them
It
pairwise.
also just seems, oh, so you just randomly,
Yeah.
like a few.
Yeah.
I mean.
Well, you can't do it for like 100 tasks, so.
Sure, yeah, just do it's massive, but then,
And it's also not clear what, like you have to project maybe onto the combinations of multiple tasks.
sure.
But empirically we found that just sampling two at a time is good.
Yeah. And if you were to combine, really constrained directions, you can step in, you know.
How did you get the normal vector? Did you?
Oh, just like that. Like you just like the way to get the normal is you just subtract, like when you have you just like take the dot product, like you take the dot product of this thing along this direction, and then you just subtract it. Right, so this thing is just the dot product of GI on the GJ direction. And then you subtract that, right? So it's like if you subtract this thing like that, then you get that thing.
So it's an order of the number of elements in the vector.
Yeah.
For every.
But it's just like a vector difference, right? So it's like imagine that you had this vector and you want to project it on the normal of this vector, right? So what you do is you take its projection onto the GJ direction, right? And then you subtract that, so then you get that. Alex, you had a question? Okay, no. Okay, so let's see if this works on a really simple problem. So we constructed this like extremely simple multitask like problem with this extremely contrived objective. But if you run standard Adam on this, you're trying to minimize with respect to two parameters, theta 1 and theta 2. Those are your two loss functions. You'll see that like this is the optimum right here. And you see that like standard Adam gets stuck. Whereas if you do this like deconflicting, it tends to like find the optimum. So this works on like a really simple problem. And then if you apply it to like multitask RL, PC grad is shown in colorblind, so I don't know, whatever that is. And across 10 tasks, across 50 tasks, it tends to like do significantly better than if you just did multitask SAC, right? Which is like just standard multitask RL. And it tends to be more efficient than if you just learned them independently. So like the algorithm we talked about last time is kind of learning things independently. The gap gets bigger with more tasks. So it's saying that it allows you to share some amount of information between the tasks while still being able to reach like 100% asymptotic performance, or not 100, but 80%. Yeah, so it's like a super simple idea. It's just saying you have conflicting gradients, project them before taking the steps. But then it still allows you to use a single policy to solve everything rather than using multiple policies. Now, this was still done for like small to medium size networks. I think the dynamics of learning might look different if you use like a 7 billion parameter model. And so I don't know the answer when we think of like a huge model. But what some of these people at Google found is that they used a much bigger model than us and they didn't need any of this stuff. So it's like, I think it's an open question on whether this conflicting gradient stuff goes away at scale. But they were trying to do multiple different tasks where they're trying to put this carrot into this bin or stack things or put away some objects, rotate them. And then they just use a huge multitask learning framework. They had some balancing of rewards and scales across the tasks, but otherwise like nothing fancy. And they were able to get like pretty reasonable multitask performance. Hard to read that plot, but it's better than the previous. So I think maybe this conclusion is a bit unsatisfying, but it's saying that I think at small scale, the distillation and gradient deconflicting, these ideas make a lot of sense. At big scale, it's not clear that they're having the same impact. So I think it's an open research question. But maybe a data point that conflicts this again is when people are doing like large scale LLM training, they're often using mixture of experts models rather than like single models. which might suggest that multitask training for LLMs is not as good when you have a single model versus mixtures of experts. Which might mean that you have like conflicting gradients or some optimization issues with multitask. So yeah. Point I want to convey is that there is some confusion in my mind about this, and we should do more research on this. But yeah, it's an interesting area of work. The point is that you can apply it to domains where you have language. This is some work from Google Robotics, where they try to solve like lots of different tasks, like picking up a soda can and navigating to the kitchen and opening the cabinets and doing a bunch of that with a single model. And so there's a single language condition model, and then they had like a language model sequence the behaviors of that model to do like longer horizon things. And you can solve like all of these different tasks with the same model where the tasks are specified by language. They didn't do as much RL. They did a lot more imitation learning, but same like resulting model perhaps. Okay, so the takeaways here are multitask RL. You can solve a contextual meta MDP where you say you're given what task you want to solve. This can help you with efficiency and generalization, but optimization can be challenging, at least for small to medium scale problems. We said it's a mixture of conflicting gradients and exploration. We can deal with it by either removing exploration or removing conflicting gradients. Right? And so the first idea was to do individual supervised learning and shared distillation, individual RL and shared supervised learning. And the second idea was to deconflict gradients in multitask RL with a shared model. Yeah, I think that's lots of open research. It's like a very unsolved problem. But yeah, that's multitask RL. Maybe let's take 2 minutes before we go to meta RL. Because you're not training your policies on the new tasks, you're just feeding in, like, for instance, in the like in these tasks, right? You just feed it in a new language instruction, and then it like tries to solve the problem. And so that like in the 50 task domain, there's not enough tasks to do generalization, but if this is in the like thousands of tasks, which is new.
Running actually do well multitask, because like I remember running experience with your Iberia or whatever. They're all under 16%.
Will it be better than multitasking? Huh? It'll be better than if you did multitask otherwise. Yeah, it's like lower than 16%. And I think even the Libero, it's like not enough data and enough tasks to really show generalization. So I think part of the problem with Libero is that you just didn't have enough data. It's like 50 demos per task, right?
Yeah.
Not enough. Nice. Yeah, that was even like 7 years.
Would the like conflicting gradients like and mixture of experts working because that would be like expect different experts like if you have like activating different experts to lead to significantly different benchmark scores if that's like one of the reasons why mixture of experts works well because I think that like they found like with one of the models they found that like benchmark scores stayed the same regardless of which expert or something along those lines.
Oh, interesting. So like it kind of helps with optimization, but it's not like you needed all the different experts afterwards, or
yeah or
like you learn redundant solutions perhaps. Right?
yeah I think so yeah.
Good question. Yeah, I guess it might be kind of like dropout in that sense, right? It's
Yeah.
like you learn a redundant solution that prevents overfitting.
Yeah.
Yeah. That sounds sensible. But I think we don't know at that scale, so it's hard to like handle it.
Yeah.
Yeah, that makes sense. Okay. Let's keep going. So we talked about multitask, and that's mostly in this zero-shot generalization type setting where you say that you're given the context of the task you want to solve, mega I, right? And it tells you exactly what you need to know. And we are mainly dealing with optimization in this setting. Like, how do we get a single policy that can solve all of them? But we're not trying to do any adaptation, right? Like, we're thinking about this as like zero-shot deployment on new problems, right? But we might not have a policy that works perfectly on new problems, but we might still have something that works well with a little bit of fine tuning, right? And so what the premise of meta reinforcement learning is that you want to go from zero shot to few shot learning, and you want to make few shot adaptation quick, right? And so the idea behind meta reinforcement learning is to learn how to reinforcement learning, just like that was meta, but learn how to reinforcement learn quickly on new problems. And so you want to like learn an adaptation algorithm that is like extremely fast on new problems. And so there's a couple of settings where you need this or you want this, right? Like the first setting is when the context is unknown or hard to specify analytically, right? So for instance, one example is when one example is when your task is not specified well by a single language instruction, but instead you really want the robot to like navigate a particular way and have a particular style, which is like a little hard to verbalize. And in that case, it's hard to like contextualize the whole task into a single omega I that you can specify. In those cases, you might need to like, it might be easier to like specify rewards than it is to specify the task, right? And so some examples are like when you have like simulated graphics characters, you want them to like behave a certain way, and it's easy to discriminate and provide human-in-the-loop feedback on what way you want. So like learning from preferences, but it might be hard to like convey all of that in a context vector that is low dimensional. And so that's one setting where this is not enough, right? Where you just like omega is not available or it's not expressive enough. And then the second setting is where your policy is not good enough. You like do not generalize perfectly. And if you're not generalizing perfectly, you need to fine tune on a new problem. Right? And so both of these settings are where meta reinforcement learning is useful. A lot of the experiments are kind of restricted to the bottom right setting, but really where meta reinforcement learning is most useful perhaps is in the top left setting, where your policy doesn't generalize perfectly and you need to adapt quickly. Right? So when we want to go from zero shot to few shot learning in multitask RL, you train your policy, and then you give it a new task, you give it a new context vector, you deploy it in the world, you run the policy, right? In meta reinforcement learning, you're going to say, I'm going to allow for a small amount of experience at test time on the test task, right? And you're going to get fast adaptation. So you're going to say the agent is going to get some experience with the world. It's going to update its parameters somehow, right? It's going to take some more experience in the world with these updated parameters, it's going to update again. And then after a few rounds of interaction, then it's optimal. And so the difference in setting is that you're allowing it to sample and interact with the world at test set. And you want it to get better with experience. Right? And so that naturally points to two things like, how do you collect data to get better? And then how do you use that data to improve your policy? Right? So if you're allowed, unlike supervised learning, you're allowed to choose what data you want to collect. Right? So a lot of the interesting questions in MetaRL are on how do you explore as efficiently as possible so that you can improve. Right? And so that's generally the difference in problem setting. We're going to think about meta reinforcement learning. So multitask RL is saying train on a bunch of tasks, deploy zero shot on a new task. Meta reinforcement learning is saying you're not going to get zero shot performance perfect, but you want to keep improving as quickly as possible by learning how to learn, right? So it's meta reinforcement. Okay, so how do we formulate this problem, right? So the idea is that you're going to collect a bunch of experience in a procedure called meta training. So you're going to collect experience across a bunch of different tasks drawn from your task distribution or your MDP distribution through a meta training procedure. And what's the result of a meta training procedure is a fast learning algorithm that you can apply to a new problem, and then you can learn quickly on that new problem. So the result of reinforcement learning is typically a policy. The result of meta reinforcement learning is a reinforcement learning algorithm. And so the point is that you can then apply that reinforcement learning algorithm to quickly improve your policy in a new problem. Right? And so the difference between RL and meta RL is one is predicting a policy, the other one is predicting an RL algorithm. And so remember the goal of meta reinforcement learning is not to predict a policy, it's to predict an improvement procedure. Or like to learn some parameterized improvement procedure And we're gonna get that from data, right? But the problem setting is gonna say, we're gonna have a distribution of tasks we have found. We're gonna try and learn an update function, like some improvement procedure, F data, that is going to be able to improve your policy on new tasks drawn from P of task, right? So the point is that your task distribution have to be the same. You can't like generalize on a brand new task distribution, but on new tasks drawn from P tau, you can improve quickly using your learned update function F data. Right, so in reinforcement learning, you have gradient-based updates. You just like run gradient ascent, right? Or you run policy grid, you run active critic, and that is your update function. Right? That is your update function that takes you from pi to pi prime to pi prime prime. In meta reinforcement learning, you're going to have a learned update function. And that learned update function is going to take you from pi to pi prime to pi prime.
So what's the control of the reinforcement
Yeah.
learning algorithm has of the procedure?
So there's a bunch of different choices that different meta RL algorithms make. Some of them like will take in policy parameters and spit out new policy parameters, right? Like the control is like you can spit out what the improved policy parameters are. Like you can take in parameters and you can spit out parameters.
Is that standard reinforcement? Like if you're tuning the actual parameters policy itself, that's
So think of it this way, right? So like, let's say this was your initial policy parameters, right? What reinforcement learning does, it runs gradient descent and like policy gradient or whatever, and gives you pi theta 1. Keep running this and you get pi theta 2. So this is your improvement procedure, right? What meta reinforcement learning is going to do is going to say, I am going to like stick these policy parameters and maybe some experience into like a big black box function. It's like a learned function, but it's like a function over functions. Right, so it's like but you can think of it as like, take all your neural net parameters, flatten it, and stick it into a function. And that function will output new neural net parameters. Right, so you can output like pi theta 1. Right, that's one way you could do this. That's not how people practically do this, but like the point is that this is just a learned update, and the learned update can take in your initial and then update them to give you a new set of parameters. And so like this is still an improvement procedure, right? It doesn't have to be gradient based to be an improvement procedure. It could be a learned improvement procedure. And so it's saying that you can just apply this procedure over and over to get from pi theta naught to pi theta 1 to pi theta 2 to pi theta 3. You're just applying F theta as your improvement procedure.
Sure. It just doesn't really appear like this. How it could appear. That's like the same thing.
But you're learning, you've learned this F theta. How do you learn this F theta? You learn it through an outer loop. Right. So like the point is,
and
that's the meta aspect, right? So like the point is the result is a learning procedure. Normally in meta RL, your result is pi theta star. Right? In multitask RL is pi theta star, and in meta RL is F theta.
So what do you, so I guess what I'm asking is like, what handholds do you have to affect F data?
So one handhold is that you can just like directly output, like you just like skip any type of gradient based improvement procedure, and you just directly output a neural net as your improvement procedure, which takes in parameters and outputs parameters. So your handhold is all of the parameters of an improvement procedure, right? The other thing you can do is you can do hyperparameter tuning. So you can say, okay, or meta RL is going to say, I learned like the learning rate and normalizer and initialization for a gradient descent procedure. Like that is a more controlled thing, but you can go anywhere from that really controlled thing to like a completely black box procedure.
If it's completely black box, it just seems like it'd be incredibly high dimensional. So
Yes,
it's very difficult
that's right.
to install.
That's right. But like it's reasonable if you have enough. But the point is, sorry,
Quantify enough.
like for instance, a lot of like big language model problems, right, are like showing like this kind of black box improvements. They're able to improve by just by like continuing to sample without ever having to do any gradient descent. This is what we call in context learning, and in context learning says that you're going to like you're going to sample in the world, get some feedback, stick that feedback back into your language model, and then you get a better performance, right? So it's like that is in some sense like a fully learned improvement procedure. And so And that is in the like what? A trillion tokens or something. So it's like, yeah, you're right that it's higher dimensional, but it might work if you have enough data on your domain. But we'll talk about some things that are more controlled. Yeah.
You would update.
So you update the update function at training time. You don't update the update function at test time. So at training time, you learn the parameters of your update function. And at test time, you just use your update function. So this maybe let me outline the procedure and let's become more clear. So in standard RL, you're going to try and learn the parameters of policy by theta, right? And that's going to try and maximize the reward for a single test. In meta reinforcement learning, you're going to say there's like an update procedure at theta. Like this, maybe let's say this is going to take in phi I minus 1, some data in the environment from phi I minus 1, and it's going to give you a phi I, right? And what you're trying to learn is you're trying to learn the parameters of the update procedure, which will quickly give you an optimal policy across the distribution of tasks in your environment, right? So you're saying there's a distribution of tasks in your environment. You're updating your policy parameters according to your update rule, and you're trying to find something that quickly gives you the optimum across that distribution of tasks.
Are we assuming the distribution of tasks will change?
Yes, we're like the training tasks and the test tasks have to be the same, or like the distribution has to be the same. Yeah. So what? You don't know. You just hope and pray. It's a good question, but that's true of like much of machine learning, right? And so the point here is that I think this is a subtle point, but it's important to get, right? So in reinforcement learning, you learn the parameters of a policy by theta. In meta reinforcement learning, you're learning there's a difference between phi and theta, right? So in meta reinforcement learning, you can think of phi as your policy and theta as the parameters of your update rule, right? And what you're going to try and do is learn not the policy, but learn the parameters of your update rule, right? And so they're saying you're going to learn the parameters of your update rule so that you can quickly get to, phi 1 star from phi naught to some update rule, right? And so you're trying to learn the parameters of an update rule. Learning the parameters of an update rule doesn't make sense for one task, because once you solved it, you solved it. But the hope is that if you learn it across many different tasks, that update rule works for a new problem. And so we'll ground what the update rule is in a concrete setting, but it's important to know the difference is that you're not trying to find a single policy that works across everything. You're trying to find an update rule that can update on new problems.
Does the update consider like different reward functions?
Yeah, different reward functions. Like you could have different dynamics, right? Like anything in the MDP is different. But that is reflected through the data that you collect at the environment. So you have to get feedback from the environment, right? Just like in standard RL. In standard RL, you'll have phi theta naught, you run it in the environment, you get some data, and then you run like policy gradient updates to give you pi theta 1, right? So you're going to take in the same, like you're still going to give it data, you're still going to give it the old parameters, but you can like learn a more efficient update rule because there's regularity in your environment, right? And so if there was no structure in your environment, meta reinforcement learning wouldn't work. But if I'm like solving, like here's an intuitive example, if I'm solving a bunch of like walk to here problems, they all have the same structure. I'm not like backflipping, I'm just walking, right? And so like the update rule doesn't have to consider all possible updates. It only has to consider a smaller set of problems, right? And so if the training distribution is infinitely wide, meta reinforcement learning doesn't work. And so that's the intuitive structure of a meta RL problem, and we'll lay out a recipe and try to instantiate some of them in time, right? Okay. So the important part is that phi I you can think of as your policy, like in the top thing, theta in the top thing corresponds to phi in the bottom thing, right? And theta in the bottom thing corresponds to the parameters of an update rule. And you're trying to learn the parameters of an update rule. And the point here is that you're going to do it, so you're trying to get the policy to get optimal as quickly as possible, right? And so the goal is to, learn as quickly as possible, or in mathematical terms, is trying to minimize regret, right? And so the intuition here is that you want to leverage regularity in your task distribution to speed up learning. So here's an example of like solving mazes, right? So if you're trying to like, you're trying to like navigate in a maze to find a goal. The goal is given by some reward, right? Navigating mazes has structure, as in you don't navigate mazes by running into the wall, right? You navigate it by like trying to explore with as much coverage as possible. So if you train on a bunch of mazes, please run. Oh no, they should run. Okay, they don't run. So I'm gonna drag it through here. So you can see that like at training time, you kind of like learn an exploration strategy so that on a new problem, you like learn how to explore efficiently. And it's not just like random search, right? You can see that like you're leveraging regularity in the fact that you're solving a bunch of mazes to explore new mazes more efficiently, right? And so the thought is that meta reinforcement learning is saying because you're restricting yourself to a task distribution, you're like learning the like regularities of the task distribution, so your update is more efficient than gradient descent. Like gradient descent works for any problem or almost any problem. Like meta reinforcement learning is only going to work for that task distribution. Right. Someone have their hand raised? Sorry. No. Okay. So the goal here is unlike RL, where you're trying to maximize reward. The goal of meta reinforcement learning is to minimize regret. And you can think of minimize regret as like trying to maximize reward as quickly as possible. And so it's like trying to maximize the area under the curve. Like reward is trying to find the highest point of the curve. Regret is trying to maximize the area under the curve, which means that you're trying to learn as quickly as possible. Right? And so reward is trying to say, hey, like get up to here. This is optimal. And regret is trying to say, like get up to here as quickly as possible. Right? And so the goal of meta reinforcement learning is to like learn as quickly as possible. Yeah. Okay. So the general structure of meta reinforcement learning problems looks like this. So you have an outer loop and an inner loop. Okay? And so the inner loop is performing an update. So it's saying, but basically it's saying like, let's take in phi I minus 1 and some data in the environment and output a phi I. Right? So it's saying previous phi I minus 1, data in the environment from phi I minus 1, including the reward and dynamics and whatever's changed in your environment, and you output a better phi I. Right? So the inner loop is performing policy updates. Yeah? And then the outer loop is evaluating those policy updates by like measuring the reward of those policy updates, right? So the inner loop is saying, I want to improve, and the outer loop is saying, how good was that improvement? Right? And so you're trying to optimize, so this is like a bi-level optimization. So the inner loop is doing an inner optimization, which is improving your policy. And the outer loop is evaluating how good the inner optimization was. And you're trying to find the best inner optimization so that the outer loop is as happy as possible. The outer loop is trying to evaluate regret, and you're trying to say, let's learn the parameters of an update rule so the outer loop is as happy as possible.
For the inner loop, you have to use like RL objective, you just do it as if we're doing.
Yeah, so that's what I think. You can like inner loop doesn't have to do RL. Like there's some inner loops that do RL and you tweak some parameters. You could also parameterize this as a big neural net, right? That takes in like phi I minus 1, some data, and outputs phi I. Like that's totally a valid thing to do. Right? And then you don't have to do RL, but some people, like some methods do. Yeah. Okay. So the general recipe looks something like this, right? So you sample a batch of tasks, you collect some data pre-update, right? So collect some data pre-update is this data. You're going to perform an update according to your parameterized update rule f theta, right? You're going to go from phi I minus 1 to phi I. You're going to collect some data post-update, right? And then you're going to see how good is that data, like how good was the reward, how good is my update rule. And then you're going to use the outer loop to go update the parameters of your update function f theta, right? So you're going to say, what I did is I like started with my inner loop is going to start from phi naught. It's going to go to phi 1. I'm going to collect some data in phi 1. I'm going to see how good was this update rule, and then I'm going to affect the parameters of the update rule to make it better, right? So it's like a bi-level optimization where you say, you're going to collect some data pre-update, you're going to update things, you're going to evaluate how good was your update, right? And then you're going to improve the parameters of your update rule update. And that's like the meta structure for the meta structure for a meta RL algorithm is something like this, where you like repeat this procedure, you sample a batch of tasks, you collect data pre-update, you perform the update, you evaluate how good was the update, then you improve the parameters of your update rule. And so, as I was saying, the point here is not to find the optimal policy. The point is to find the optimal update rule. And so really you care less about phi than you care about theta. Right? So this is your update rule. Okay. So that's the general structure of a meta RL algorithm, right? Remember, the goal is to learn a fast learning algorithm.
The big difference. So the phi i's for all the i's.
Yes, for all. So like you run it differently for every task. Right? Because the updated parameter will be different for every task, right?
It's to calculate all those.
That's
for all
right.
those.
That's right. And you can run it one step, you can run it many steps, right? But in the inner loop, you can choose to do whatever sort of update you want. The outer loop is going to evaluate that update per task. Right? And then you want to find something that's good in expectation across all the tasks. Yes, you can get stuck in local minimum for everything. That's how we do most of our, right? You can get stuck in local minimum for even single task startup, right? And so you're totally right that the optimization and multitask meta RL is harder than for single task startup. Solutions that people do is like they have a curriculum of tasks, or they will try to like warm start with some like improvement procedures that write by hand. Like those kinds of solutions work, but you're totally right, it's harder to problem. But the problems are kind of like existent in both RL and in meta RL. Good question. Okay, so the main design choices we're going to make is like, what is F theta? Like Pavel is saying, like you can choose like the neural net is going to be a huge high dimensional space. You can like have a more structured update rule and then pick some parameters in that structured update rule. And so the choice of F theta is important. And then you want to pick an algorithm for the outer loop optimization, right? And so like different meta RL algorithms are going to choose different things here. Right? We have 18 minutes, so we're not going to get through all of them, but let's get through like one or two of them. And each of the different algorithms are just going to have a different choice of F theta and a different choice for outer loop optimization. Right? So if you want to design a new meta RL algorithm, think of this recipe and design a new F theta, design a new outer loop optimizer, and you get a new meta RL algorithm. And so like the different choices in your inner loop are to have like a big neural net that takes in past parameters and gives you new ones. Has some latent variable model that does like some sort of posterior inference, or literally do gradient descent by tweaking some set of parameters in gradient descent. In the outer loop, you can use what we already learned. You can use policy gradient, you can use factor credit, you can use multiple stuff. But like every meta RL algorithm is some mix and match of these things. Okay. Does that kind of parse? Like the whole point is that you want to find the best update rule across a set of tasks, and you're going to do this through this bi-level optimization. Okay? Inner loop is doing an update, outer loop is evaluating it. Okay. So let's start with memory-based meta RL, which is probably the easiest one to understand. But it says that make the update rule forward pass of an RNN. So it's saying that like your inner loop in this update, like think of your update as something that just takes in past data, right? And which includes like past SA S prime R. Let's say you've got a series of SA S prime R. What it's saying is it's going to take those things in and produce a new action, right? And you produce a new action, you evaluate how good that action was. So all it's saying is that your inner update rule is just going to be an RNN that takes in a past history of states and actions, RNN, and gives you a new action for a new state. That's it, right? So it's saying that the inner F theta is just a big neural net. It's not literally going to take in parameters, like I was saying. It's just going to take in history of states, actions, next states, and rewards that you took in the environment. And it's going to try and output a better base. Right? And so it's just like implicitly, this RNN is representing an improvement procedure, because you're saying, oh, no, I took some suboptimal SAS prime R's in the world. My RNN is going to try to output a better A, right? And so this is an update rule that's going to take suboptimal A's and give you better A's. And so your memory-based meta RL procedure is just an RNN that takes in past SAR pairs, in your trajectory, it outputs for a new state, outputs a new action. Right? But the important thing about this is that it has to take in reward. Like if it can't take in reward, it doesn't know how it can improve. It doesn't know that it's doing suboptimally. So your RNN has to take in state, action, next state, and reward. Right? And like based on that reward, you can tell that you're suboptimally and you need to do better. And so all you're going to do is in your inner loop, you're just going to maintain the hidden state of your RNN, right? So you're going to say your RNN is taking S, A, S prime, and R. Yeah, so you can see that it's taking S, A, S prime, and R. And you maintain the hidden state of your RNN across time steps, right? And the whole point is that if your RNN weights up, parameterize an update rule, then as you like roll out your RNN further, your actions will get better and better and better. And in your outer loop, you just try to say that this RNN has to like get to optimal actions as quickly as possible. So you just run a policy gradient objective in the outer loop, right? And so if we go to our recipe, right? So we're saying that like the inner and outer loops are just like this big black box RNN, right? And so you can almost think of like policy gradient, where your policy is parameterized as an RNN, which takes in past reward, and is optimized across many different tasks, already does meta-RNN. So the point is that because you're trying to say, maximize your sum of rewards, and your policy is like an RNN, which takes in S, A, S prime, R, your policy has the ability to change over time, right? As opposed to a policy that just took in S and gave you A. Like here, I have a policy that can take in S, A, S prime, R from the past. You can see what you did wrong and get better over time. And so all that this memory-based meta-RL is going to do is going to say, sample a batch of tasks, collect data using an RNN, where the RNN takes in state, action, next state, reward, your whole history, right? And then you're just going to try and say maximize the sum of rewards for that RNN across many different episodes. So you're going to say the RNN runs across many different episodes. So like you can think of each of these as an episode, right? So you like tried once in the maze, and then you get to try again, right? But you're going to like keep your hidden state consistent in your RNN as you go across many episodes. The point is that it has seen what you did. It's seen that it wasn't good enough. And because it's in the hidden state, the next time you try it, it's going to like be better. Right. And so your RNN is going to try and maximize rewards using policy gradient in the outer loop. But all you want to do, like you can think of it as just doing RNN policy gradient, where you feed in rewards into your RNN, and you're trying to maximize rewards across distribution of tasks. That's it. Right. And so like if you ever saw the OpenAI cube result, it kind of does something like this. Like DeepMind had some new results which do this, but like this is extremely simple because it's just like RNN training skills with this thing skills. But as Pablo was saying, it has no structure, and if it has no structure, it means it's a huge high dimensional problem, which means it's going to need a shit ton of data. So it's not going to work for real world problems, but it might work for like games that you can simulate a shit ton of games for, right? A backprop through time. Yeah, sorry. Yeah. And then at test time, so you do this at training time, and at test time, you don't need to do any updates. You just run your RNN. You just run your RNN where you feed reward back into your RNN that you keep running, right? And so like you ran one episode, you fed all the rewards back in the next episode it'll be better. Because at training time, you literally trained it for the RNN to get better over time, right? And so does this work? Kind of, right? So if you apply it to these, Jesus, okay, applied it to these games, what you'll see is that it like it learns how to explore in a very targeted way, right? So it only gets reward when it reaches the box on the right. So it learns to explore in a very targeted way so that the next time it tries things, it kind of like directly goes there, right? So the RNN learned to explore, and then once it saw reward, it learned that it should just like update its policy to keep going there. So like every episode after, it's going to keep going. But the point is that all of that was done through the RNN updates. You didn't have to do gradient descent. Yeah. Yeah. Yeah, you can change the location of the box. So like it'll have one episode that explores here, it doesn't find it, right? And then the RNN will say, okay, like it wasn't here, let's explore somewhere else. And you just run it in many episodes. But like as Pavel was pointing out, I think it's a doubly difficult problem because yes, because you have to represent policy update, but also because you have to learn how to explore Like you have to learn to search basically. And if you like, the tricky part about meta exploration here is that you have to like know how to search to learn how to search. Right. So it's like if I didn't know how to search, then how would I get good enough data to like solve this problem? Right? So that's what makes meta hard. So the nice parts about this is that it's simple and easy to implement. It's generally stable because it's running PPO with an RNN, but it doesn't have any guaranteed improvement, right? If you go out of distribution, like who knows if that RNN will get better or not? You're just running it forward. And when it doesn't get better, you're screwed. You have to go back to like gradient descent or something. And it doesn't really work out of distribution unless you have like internet scale data. And so that's what makes this kind of tricky. How much time do we have? Like 9 minutes. Okay. I'm gonna like convey the idea super quickly here. Apologies. The thought is that, okay, like we had this black box RNN. The RNN was not necessarily convergent, it doesn't get better. What if we like made it into a procedure, like Paul is saying, like make it structured so that it'll get better, right? And so the idea here is that you can force F theta to be a convergent optimization algorithm like stochastic gradient descent. So your update rule can be stochastic gradient descent, it can be policy gradient, it can be active critic, it can be whatever you want. And then the natural question to ask is like, what are the knobs that you can tune in your update rule? If it's gradient descent, it's like that's already an algorithm. Like, what can you tune to make it more efficient, right? And so we're going to say in our update rule, F theta, the procedure is going to be gradient. This can be any update rule you want, right? So let's say it's going to be gradient descent, right? So it's going to be phi I is equal to phi I minus 1 plus the gradient of your loss function times some learning rate, right? With gradient descent. So what are the knobs you can tune? Obviously, there's like things like learning rate and hyperparameters and these kinds of things. But in this next line of work, they had a kind of more interesting idea. The interesting idea was that what you can change is the initial parameters from where you do gradient descent. Right? So it's saying that like gradient descent is going to do gradient descent, but you can change the point from where you start. Right. And so it's saying that like you try to find an initialization which is most amenable to fast gradient descent. And so they try to find an initialization of parameters theta, which are as gradient descentable as possible. Right? And so the thought is that you try to learn an initial parameter theta such that when you learn, such that when you update that parameter with gradient descent, like literally gradient descent, like the phi I that you get is as good as possible. Right? And so doesn't seem like this should work, but it like works surprisingly well, right? And so the point is that the knob that you tune is the initialization from where you start gradient descent. Normally, you just randomly initialize the network. What you learn from training across all of these tasks is an initialization, and then at test time, you just do gradient descent to get to different tasks, get to the optimum for different tasks, right? And so the nice part is because your inner loop is just gradient descent, it has lots of structure, might need less data, and you can keep running this procedure. Like at test time, like an RNN may not get better, but gradient descent will get better. And so the nice part about this algorithm is that it just learns the most fine-tunable parameters such that one step of gradient descent is good, right? And the nice part about gradient descent is that it's differentiable. Right? You can just take the gradient of this thing. It just has a 1 second derivative in there, but otherwise it's all gradient, it's all differentiable, right? And if you use PyTorch, you don't even have to compute it. And so the pseudocode here is that you're going to sample a batch of tasks. You're going to collect data pre-update from pi theta with your initial set of parameters. You're going to perform an update with gradient descent. You're going to evaluate how good that data was, and then you're going to backpropagate through gradient descent to find the best set of parameters, right? And so I'm going to skip the math, but basically you try to optimize for this thing, and then the update rule is fixed, right? But in some sense, the initialization affects how good the update rule is. Right? And so you try to find the most fine-tunable set of parameters. And yeah, I thought it was surprising that it works, but basically you like have these half cheetah tasks where it's trying to run forward and backward. It doesn't know if it has to run forward or backward, but with one gradient step, you can see that it's like learning. Normally this would take hundreds of thousands of gradient steps, but with one gradient step, you can see that it learns to go forward and backward pretty quickly. And it continues to get better over time, right? So if you look at the number of, it was trained for one gradient step, but then you can apply multiple gradient steps to get it to be better and better because it's a convergence update, right? And yeah, so this was all the rage in 2018 and 2017. But yeah, it's a cool algorithm. It's just saying inner loop is gradient descent. Okay, so there's more things you can do with latent variables and so on. Let's skip all of that and show you guys some more cool videos. So if you use algorithms like this, you can adapt to like different types of floods. So here you have like different types of floods. Each of them have slightly different dynamics. You can't like generalize your shot. But instead, if you just do a few steps of fine tuning, like 10 to 20 minutes of fine tuning, you can do extremely well across lots of different shapes in the real world, which is nice. This is another one where you do something similar, but you learn how to adapt to like changes in your morphology, right? So like they love doing these things with this little cockroach, but a cockroach tends to lose limbs, like limbs stop working or something cracks, and they're able to like use the same adaptation procedure to adapt online to like changes in morphology or things like that. Or you like change the payload or change the friction of the environment, it tends to adapt, which is nice. So the takeaways I kind of want to convey here is that meta RL lets you go from zero shot to few shot. You can kind of optimize most meta RL algorithms as this bi-level optimization where you have an update and then you evaluate how good the update is in your outer loop. And it allows for adaptation where you don't know the context or you may not generalize perfectly, right? And so for those of you who are interested, it's like very related to how POMDPs work. Like there are like lots of meta RL solutions are similar to POMDP solutions. Okay, so the landscape can be kind of understood as like multitask is sitting at zero shot, meta RL is sitting at few shot, and then fine tuning and policy gradient, all of that is sitting at many shot. Right? And so we have different types of inference algorithms. We did memory-based things, we had variant-based things. You can do like latent variable models. There's lots of different ways to do it, but all of them are kind of like at different points along the spectrum of zero shot to few shot to many shot. Lots of readings. Some of them are mine, some of them are other people's, but I think they're all interesting. Take a look. Cool. So some takeaways from the class is we've finished all the boxes. That's exciting. And what did we learn in this class? Right? We learned policy gradient algorithms. We learned policy gradient, dynamic programming, model-based RL. We learned how to unify these with control as inference. Right? And then we use that control as inference framework to explain inverse reinforcement learning. And we talked about exploration, which are elements of making a practical RL algorithm. And then we talked about multitask and meta RL, which is more researchy, more frontiers, right? But the hope here is that we kind of like covered some of the foundational methods in RL. And if you want to think about the big open problems in RL, these are some that I think are interesting, right? Biased, of course, but like there's no data in RL. Where does the data come from? It's an important question, right? Like supervised learning is using trillions of tokens. We have like 1,000 trajectories in RL. It's the same. If you want to do RL in the real world, you have to think about safety. You have to think about efficiency and doing it around people, right? And so that's stuff. We haven't really figured out how to make RL algorithms generalized, right? So we have to think about generalization, what it means, how do we formalize it, what assumptions can we make? And so, yeah, generalization is important. And then if we can't collect enough data, like can foundation models help bridge the gap and where do they fit? I think it's an interesting question. Okay, I think that's it. Yeah, it's been a pleasure. Yeah, thanks for listening. Appreciate it. All right, and see you Tuesday. And grab some donuts on your way out.
Thanks so much.
Yes, of course, yeah.
Fun.
I'm glad to hear it.
Yeah, that's kind of worse than I expected. But I was like, a lot of math.
Yeah.
Cool, I kind of.
It kind of fits after a while.
It really does. It's kind of crazy.
Yeah.
Is there any, like, I'm gone before, but is there any other classes that expand here? Or is it?
Kevin Jameson's classes is interesting and expands learning, interactive learning. It's more theory.
My friend taking that right now, and he's like.
Yeah.